Hey everybody, welcome to chapter 8. So in the last chapter and for a while now, we've been talking about trig functions, and sometimes we get to a place where we'd be asking ourselves, sine of x equals 1, and you guys would solve for that particular x, right? Like this is an angle, you'd give me an angle, and you'd say, okay, well, if I want sine to be 1, that could be at pi over 2 or any wrap of pi over 2, right? We've been solving these. But the problem comes in when, what if we don't know the value on the unit circle exactly? So like, what if it's 0.72, for example, and we want to know, there's definitely a place on the unit circle, because here's sine equals 1, and here's sine equals 0. So as the point travels along, there's going to be a point when it is 0.72, but the question is, when is that? And what angle would produce that, right? That's what we're really looking for, because this is an angle in here. So you probably have talked about in the past how to undo certain things or inverse functions, right? So for example, off to the side here, if I had like 2x equals 10, I would say, okay, well, what's the inverse of multiplication? You guys would say division. So we would do the inverse operation to solve and get x equals 5. Or let's see, we've also done, I mean, you could do addition, you could do subtraction, you could do logs and natural logs. There's lots of functions that use the inverse to cancel something out. So we have the same scenario for trig functions. So that's what we're going to talk about in chapter 8 is inverse trig functions. Okay, so let's go back and talk about basic inverse trig functions for a second. Okay, so if you want to find the inverse of a function, then instead of going from x to y, you want to go from y back to x, right? Again, if you were to leave your house, go outside, walk to the school, for example, if you were to invert that, you could go from the school back to your house, right? You would just undo each step that you had done along the way. Okay, so those are inverse functions. Okay, let's review a little bit how we find those, and then I'll talk about determining whether things are actual functions within the inverses. Okay, so how did we find an inverse again? Well, one easy way that you would have done this in the past would be to take the original function and switch what used to be the input with the output. So here, see, I'm switching the x and y's places. Now, for me personally, when I flip them, I like to write this. This means y inverse, and it lets my reader know that the answer I'm about to get out is the inverse of the original y. You do not have to do that, but that's just a math notation that can sometimes happen. So we switch x's and y's places, and then we resolve for the new y value. So many of you, if I asked you to go backwards, if I said, okay, the original function is times 5 minus 3, a lot of you would say, well, then I would add 3, divide by 5. Like a lot of you can do that probably in your head. You can get that logically, not a problem. But obviously, some of these get more difficult. Okay, so how do I take that idea of inverse functions and apply it to trig functions? Well, it's the same idea here. We're going to say if y equals sine of x is my original, then if I switch x and y's places, then technically this would be its inverse, right? Again, we're not going to restrict the values just yet. We'll talk about that, making it a function in a moment. But we wanted a way to notate that, right? Because we wanted to be able to solve for y equals. And so that's where we brought in this idea of sine inverse, or arc sine is another word for that. So this is that notation. It looks like to the -1 power, but it means inverse. So be careful that you're not confusing that with a power on the trig function. So this is sine. This is not the same. Sine inverse is not 1 over sine to the 1 power. It's not that. That is not what this notation means. And because there is some ambiguity, that's where arc sine came into play. So arc sine just means sine inverse, or the inverse of sine. Okay. And again, what it's solving for is the angle that produces a particular output. So this part is a really important piece of that. You want to make sure that you understand when I do sine inverse of a value, this answer is giving me the angle. I am getting the angle out because, again, originally it was like sine of theta equals y. Then you did sine. You can think of it as you took the sine inverse of both sides. If I took the sine inverse of this side, it's a little tricky because I have to have it in front. So I'll do that. These two cancel and give me the angle. And so this is the notation, sine inverse of y. So again, sine inverse of something is giving you out the angle that produces that value. Okay, so let's take a quick look at some of these graphs. So the pink graph that I have here is the original sine. So this is original sine. If I were to graph sine inverse, that's the yellow graph, right? All I did, guys, remember, to graph the inverse, I literally switch x and y's places. So this is sine inverse. Okay. If I'm graphing sine inverse, notice like this point, which is pi 1, for example, now becomes 1 pi. This point on sine, which used to be, let's think, that would be pi comma 0, would now become 0 comma pi. So there's that. And then so on and so forth. So I could graph the inverse pretty easily by just switching the graph of the original. But here's the issue that we have with the inverse trig function. It's not a function. Why? Well, you guys know if you want to test to see if something is a function, you run the vertical line test. And the original sine function is absolutely a function. There's no repeated x values, so you're good. As soon as I create the inverse sine function, which again is what this guy is, if I create the sine inverse function, now I have a lot of places where it's repeated because now you have it horizontally along the y-axis. So there's plenty of places like here, for example, this value gets repeated over and over and over. Okay, so that's an issue. We don't like there to be ambiguity. We want things to be a function. So what we did as mathematicians is we said, okay, we're going to pick a particular part of that inverse graph and we're going to restrict the values so that it does create a function. And to make it easiest, we wanted to pick the section of this inverse graph that was the closest to 0 but had all the values. So you'll see there, I'm actually going to do it in blue. So I picked this section, or mathematicians pick this section of the graph. It covers all the x values you need, because see that, and then they start to repeat themselves and so on and so forth. So it covers every x value that would work, and it goes from negative pi over 2 to pi. So sine inverse has a domain, x values. The x values run from negative 1 to 1, which should make sense. Think about this, guys. If you're switching x and y's places on the old graph, it fluctuated between 1 and 1. So when you flip it, the domain fluctuates between negative 1 and 1. The range is the one I had to restrict, the y values. So I restricted the range to only go from negative pi over 2 to pi. That's if I want it to be a function. And when we do this, we actually use a special notation. Instead of a lowercase, we use an uppercase sign. So if we use the uppercase, we're referring just to this specific tiny portion of sine inverse. If I use a lowercase, I'm referring to every single version. So I'm going to get multiple answers out. Okay, so let's take a look at some of the other ones. Here's cosine. So my cosine graph, here's the original cosine. Here the yellow is cos inverse. Now cos is different because it's a different graph. So when I wanted to make sure that I went the whole, the whole x values, right? I didn't want to repeat anybody, and I also wanted to be closest to 0. So that's why I started here. I didn't do this section because then I wouldn't have these parts. So I did this guy and I did that guy, and then after that it would repeat. Same thing down here. Why did I choose to do this and not this? Well, these are positive values. So again, we're trying to choose the nicest principal values that are smallest and positive. So this range goes from 0 to pi, and again, left to right is 1 to negative 1. So what does that mean? Capital cos inverse has a domain. Again, left to right is from negative 1 to 1. It's the opposite of the original. The original's range was negative 1 to 1, the new domain. The range was all reals, but now that I'm doing capital cos and just getting these principal values, it only goes from 0 to pi. Okay. And then last but not least, tangent, which I know is very overwhelming. The pink graph, again, is the original. The yellow graph is the inverse. Obviously, there are lots of places it would fail being a function. So what we did is we picked this guy in the middle. There, that one runs all the x values I need without repeating any. If you remember correctly, guys, original tan, regular old tan, had a domain that was restricted because you would lose every single vertical asymptote, right? So it was like, all reals except you couldn't be like, pi over 2 plus n pi. And then the range was all reals. So if I switch their places, because again, this is for the original, if I switch it for the inverse, as you can imagine, now the domain is all reals, just like you see here. So for tan inverse, your domain is all reals. You can plug in anything from left to right. But your range is only this part, if I'm doing capital tan inverse. So either capital tan, or if I'm writing it as arc, it would be a capital A. Because remember, these both mean inverse. Oops, sorry, there's no inverse symbol. I'm doing it that way. There we go. Okay. So this goes from, it's what would have been the old asymptote to the old asymptote. So remember, this old asymptote was pi over 2 and negative pi over 2. So it goes from negative pi over 2 to positive pi over 2. Now, why would I put parentheses there? Yeah, this negative pi over 2, it never reaches it because it's an asymptote. So is this one. This happens to be horizontal because I switched the order. Okay, so that's why it's not inclusive. Okay. So, when you are putting things into your calculator is programmed to only give you the principal values, meaning it's going to treat it as a capitalized inverse trig function. So for example, if I were to graph sine inverse, notice it does not give me all those values forever and ever. It only gives me the principal values. So again, from negative 1 to 1, and from negative pi over 2 to positive pi over 2. So it's only, when you do a sine inverse on your calculator, it's only going to give you the answer, one answer, and that's the answer that fits on that function. Same thing for cos inverse. You can see here, cos inverse goes from 0 to pi on the y-axis, again, negative 1 to 1 on the x. And then tan inverse goes from all reals for the x values, but y values, it only goes from negative pi over 2, non-inclusive, to pi over 2. So again, there you can see those principal values graphed there. Okay. So one little drawing that might help you to kind of get an idea for how we find the inverses, capitalized inverses. See how these are all the capitalized ones? Like, for example, if I was doing capital cos inverse of 1, remember, this is asking for what angle of cosine do I get? 1. So your output is the angle. This guy is an angle. And you're trying to figure out what angle would give me 1. Okay, so if I was doing capital cos inverse, you guys should remember from the previous graphs that we did today, cos inverse is allowed to go from 0 to pi for its outputs, which is what I'm looking for here. Or you can think of that as quadrants 1 and 2, right? And if I want it to be a positive 1, I know that the positive stuff is over here, the negative one's over here. We'll get to practice that a little bit more as we do them. And so then I can figure out where that is. This particular cosine is only 1 at the angle 0. So that final answer here would just be 0 or 0 degrees or 0 radians. Same answer. So what other functions only exist in quadrants 1 and 2, technically, for their inverses? Well, the reciprocal of cosine does, secant, that's easy to remember, and then cotan. I think cotan is easy to remember because cotan has cosine on top. Okay. And then there are 3 functions that go from negative pi over 2 to positive pi over 2 for their inverses. You already should know sine and tan, and then cosecant because it's the reciprocal for sine. Again, as we do more of these, we'll get better and better. No, nobody's ever in the third quadrant because it would have wrapped on itself and then it wouldn't be a function anymore. Okay. So let's try some. Okay, so if I want to do the arc sine of 1/2 as opposed to lowercase arc sine, so I'm going to do both and we'll show you what it means. Remember, if I take arc trig, by that I mean this could be arc sine, arc cos, arc tan of something. This means the angle whose trig value gives me blank. Okay, so let's see. So this is asking, arc sine of 1/2 is asking what angle, I should be getting out an angle that gives me 1/2 for sine. Okay, the first thing I would do if it were me is I would figure out, okay, what reference angle is this? So if sine is 1/2, remember that would mean the y value is 1/2. Then I know it's a 30, 60, 90, and if this side, the y value is 1/2, it's a 30. I'm going to use radians, so I'm going to call this pi over 6. That's the reference angle. Now the question is, am I in the right quadrant? Well, capital arc sine is only allowed to be in either 4 or 1, negative pi over 2 to positive pi over 2. It's positive, so I know it has to be in the first quadrant. So my answer there is just pi over 6. Now, how is that different to lowercase? Remember, lowercase allows me to choose all angles that would work. So I have to think, okay, well, I know that a pi over 6, a 30-degree reference angle works. Where else is sine positive? Also in the second. So I need every version of those 2 angles. So I could say the angle could be, like I would do a theta maybe. Well, I guess I could do this. I could say pi over 6 and 5 pi over 6 and every wrap of those. So I would say plus 2 pi n. So then this would give me every wrapped version of that. Very different. I should only get one answer here because it's specific. It's a function. I should only get one output for each input. Here, I'm going to get every wrapped version of the angle. So what if it was negative? Well, a lot of this stays the same. If it was negative, remember, capital arc sine is only allowed to be in 1 or 4. Because it's negative, I know it's going to be in 4. I know the y value is negative 1/2, which is still a pi over 6 reference angle. But if it's in, remember, we had to go from negative pi over 2 to positive pi over 2. So this is negative pi over 6. It's that reference angle down here. Now, no, you cannot call it 11 pi over 6 because capital arc has to go, if you want to talk about something in the fourth, it has to be from negative pi over 2 through 0 to positive pi over 2. Remember, that's what the graph looks like, if you can recall the graph. So you don't have the choice of 11 pi over 6. That'd be way over here. If you want to talk about this, you have to refer to it as negative pi over 6. So anything that you want to use in the fourth quadrant will always have to be the negative version of the angle. Just keep that in mind. Okay, how about lowercase? Well, lowercase arc sine negative 1/2. Sine is negative 1/2 here, and it's also negative 1/2 in the third. For these two, again, it's kind of your choice. You could call this one negative pi over 6 if you want, or you could call it 11. And then I need to go to that pi over 6. That pi over 6 is 7 pi over 6. And I could be both of those and any wrap of both of those. This one, it doesn't matter how you discuss them because you're going to do every single wrap. This one, it does because of the capital letter. Okay. So when it's not capitalized, we call this the general solution because you're giving me every single solution that could work. And then this one is a specific solution, right? It's an exact specific solution. Okay. Let's try these. Arc tan of 1. Well, let's think about this. When is the tangent 1? Like that's the first thing I would ask myself. Tangent of what angle gives me 1? The reference angle would be 45 or pi over 4. Now you have to ask yourself, since it's capitalized and positive, where is that allowed to be? Tan is allowed to be in the fourth or the first, and it's positive in the first. So this angle could only be pi over 4. It can't be any other version. Let's try this guy. If you want to pause, you can. This one, arc cos is negative 1/2. The first thing I would do is figure out where that's allowed to be. Capital arc cos or inverse cos is allowed to be in 1 or 2. 0 to pi, if you remember, outputs. It's only negative here, so I know it's going to be here. Cosine is the is the x value, so that would mean this side has to be the 1/2, which is this is the short side, and that's the long side. So that means this angle is the 60-degree angle, or pi over 3. Now that's the reference angle, guys. Pi over 3 in the second quadrant is 2 pi over 3. Okay. So let's look at some ones that are a little more complicated, and we'll do more of those other examples in class. Let's look at some of these. Now this one, notice I don't just have an inverse function. I have an inverse on the inside, but I have a function on the outside. Okay. The way that we attack these, I'll do one, and then you could probably handle the second one. The way that I attack these problems is I think to myself, okay, if I'm doing an inverse of a trig function, what is that giving me again? Like, what is the output if I do an inverse, or what am I getting out? I'm getting out an angle. So what I would be thinking to myself is this is really asking me the tangent of a particular angle. Now, the problem is I don't know the inverse sine of 3/5. That's not like a nice one on the unit circle. 1/2's nice, root 3 over 2, root 2 over 2, those are all nice. This is not. So what you can do is use this relationship to make a triangle. How? Well, it tells you the sine ratio. It says that the sine ratio is 3 to 5. And it's positive and it's capital. Remember, sine is positive in the first quadrant when it's capitalized. So sine is opposite to hypotenuse. So that would mean I know that the ratio is 3 to 5 for this angle. That's what this is saying. The angle that gives me a ratio of 3 to 5 for sine. Well, you can finish getting the missing side in that triangle. Just use Pythagorean theorem. 4. Now, can you give me the tangent of that same angle? Yeah, and you never have to find the actual angle, guys. The tangent ratio would just be this opposite side over the adjacent. So the final answer is just 3/4. You never had to solve for the angle. Never. So let's try this next one. Again, this inside is an inverse trig, so I would first rewrite that as cos of an angle, and then I'd figure out what my triangle looks like according to this. Arc sine, capital, remember, sine inverse is only allowed to be in 1 and 4. Because it's negative, it has to be in the fourth. Okay. Sine, opposite, over hypotenuse. Now you know it's negative. Which one of these has to be negative? I'll give you a hint. It's never the diagonal. And it makes sense anyway that the y would be negative. Once again, last side, Pythagorean theorem, is 4. Be careful. Sometimes this number you fill in, because of what quadrant you're in, will be negative and you'll have to force it. I didn't have to force the 4 to be negative because it's on the positive x-axis side, but be aware. So what's the cos of this same angle? Adjacent over hypotenuse, 4/5. Okay. Now we're going to mix it up. This time, I put the inverse trig function on the outside. So let's look and see how this is different. Well, this time this is not giving me an angle. This I can do. I actually know the cos of 5 pi over 6. So the first thing I'm going to do is find the cos of 5 pi over 6. Okay. Cos of 5 pi over 6 is in the second quadrant. It's a pi over 6 reference angle, which means the x is larger. So root 3 over 2. And don't forget, it's negative there. So then your final question is, what angle gives me negative root 3 over 2 for sine? And it's capitalized. The first thing I would do, ask myself what quadrant I'm allowed to be in. Capital arc sine can be in 1 or 4. It's negative, has to be 4. And the sine, which is the opposite or the y side, is root 3 over 2. That's definitely a 30, 60, 90 triangle, and this side's bigger, so that's the 60-degree reference angle. Remember, though, you have to refer to it as a negative in the fourth quadrant, so that'd be negative pi over 3, or negative 60. Okay, let's do this one. Cos of 4 pi over 3. Cos at 4 pi over 3 is in the third quadrant. Pi over 3 reference angle, my cos is shorter because this is the longer side at a pi over 3. So this would be negative 1/2. So this is the same as arc cos of negative 1/2. So I did the inside, now I'm going to do the inverse. Now this is interesting. You might think, well, these undo each other. Well, let's look. Because capital cos inverse is only allowed to be in 1 and 2, it's not going to end up in the same angle or in the same quadrant. Which one of these two is cos negative? Second. So this is cos being 1/2 or negative 1/2 is a 60-degree reference angle. So it is a pi over 3, but it's a pi over 3 in the second, not the third quadrant. So your final answer here is that the only choice for that angle is 2 pi over 3. It's the pi over 3 reference angle here. Oops. Okay. We've just got a few more, and then I think we're done. So for this one, arc sine of root 3 over 2, this is as, now this one, you can do this one. You could make a triangle, guys, or you could just do it. Arc sine of root 3 over 2 gives me the angle first, right? So it's asking you, when is sine root 3 over 2? Sine of what angle? Well, that would mean that the y value in your triangle is root 3 over 2. That's a 30, 60, 90 triangle, and this side's bigger, so that would make this angle a pi over 3 reference angle. And it is positive, so you know that it's in the first quadrant, capitalized, right? Arc sine is only allowed to be in 1 and 4, so it has to be positive root 3. Or, I'm sorry, positive pi over 3. Oop, for the angle. I got ahead of myself. So then I have sine of pi over 3, and the sine of pi over 3 is root 3 over 2. So this one, it came out the same. Like these two did seem to cancel out because I did get root 3 over 2 back. Let's look at what happens when the arc sine is on the outside. So once again, sine of 4 pi over 3, this one you should know. The sine at 4 pi over 3 is root 3 over 2, it's negative. But again, when I do the arc sine last, my only options are 4 and 1 for where it could be. And to be negative, it has to be down here, which means it's still a pi over 3 reference angle, but I have to refer to it as negative pi over 3. So what have we learned? This is an important distinction to make. If the arc sine is on the outside, these do not just cancel, meaning you can't go, oh, it's 4 pi over 3. No. But if the sine is on the outside, like if the arc sine is on the inside, then they do cancel, and this will be correct every time. We'll talk more in class about how that works. We'll look at some more examples and see, but that's something to note. If the inverse is on the inside, they do cancel, assuming that it's, like they're the same trig function, like sine and arc sine or cos and arc cos. But if the inverse is on the outside, they don't necessarily come out to the same value. You have to finish solving. I will cover this in class, this guy, what happens if the angle is not a special angle, because that's a little more in depth. So I will talk about that together. But that is something that's coming. If you want to think about maybe how you would do that, you could think about creating triangles and whatnot, but we'll do that together in class. And then I will also touch base in class on what happens if I use letters here rather than numbers. So that's coming. And then eventually we're going to get into these kind of crazier problems. So I'm going to cover that in class the next time that we talk or on a next video, but I won't do that here. I'll let you kind of get your bearings with some of the basic inverse trig functions. So good luck, and I will see you in class.